How are we doing?
Yes.
Anybody okay? Oh, get the hell out of here!
If you need a pointer.
If I need a pointer, no, I don't think so. Okay, just going to say this is an experiment in whether I can give a totally impromptu lecture about an issue which is, I think is interesting, and I did give this in the next room, and Naresh
You gave it to the faculty.
He gave it to about 3 or 4 of them, and Naresh thought it was sufficiently interesting, and one or two important scientific issues about how one addresses data. But let me tell you what it is. It's actually the origin of life, so it's an important issue. And I'll tell you the story is a little bit that surrounds it. It's about the scientist Fred Hoyle. And how many of you have actually heard of Fred Hoyle? Let me just check. That's 1, 2, nobody else. Okay. Well, in the 60s and 50s, Fred Hoyle, Sir Fred Hoyle, fellow of the Royal Society, was a very famous astronomer. He died not that long ago, and he was famous for suggesting that carbon had a special resonance in the sort of nuclear spectrum, an excited state, which enabled the triple alpha process, in which 3 alpha particles can come together to form carbon, could actually have a significant cross-section. Okay, and there are plenty of suggestions for that. Okay, so now why is that important? And that's important, in case you didn't come to my lecture about a year and a half ago, is because in the nucleosynthesis of the elements, in a star you get hydrogen squeezed into helium, or protons into helium. And then you can't get to carbon by a 2-body collision, okay? If you have carbon, you can go to oxygen by carbon-12, adding an alpha particle, you go to 16. But there's no stable element at number 8, okay? And there was a paper by, I think, Salpeter, said maybe there's a metastable lithium or beryllium-8, but there was no stable nucleus there. So had there been one, it would have gone to carbon. Okay, we get carbon. But we're all sitting around, so obviously carbon's formed. And it was quite clear at that time that nucleosynthesis was the way that the elements were formed. You can form all the elements from carbon up to iron inside a star, and that was fully worked out. And in fact, Hans Spater, who died last week, I think, is obituary, big columns in the New York Times, he's very famous, wonderful scientist, very charming man, I understand, I never met him, very humanitarian guy, and he was involved in answering these questions about nucleosynthesis in stars. Anyway, the problem was, how do you get carbon? And Hoyle was a very eminent scientist, was very famous. And he sat down and realized, well, here I am, sitting here contemplating myself and my navel. So there's obviously something special about carbon that gets over this. And he surmised that there must be an excited state of carbon-12, of the nuclear state, so that the cross-section of the metastable element 8 might last long enough so that there was a fairly high cross-section into this excited state for reaction with an alpha particle to give carbon-12. And he predicted what that energy would be because he knew what the energy of carbon was, carbon-12, the ground state, and we knew what the energy of 3 alpha particles in MeV should be, and he predicted this, and Fowler at Caltech didn't believe it, but looked, and they found it exactly there, where he predicted. And that is considered the first anthropic result that's ever been made. In fact, saying the anthropic principle says, isn't it interesting that all the parameters of nature, Planck's constant, the velocity of light, are all there to produce us? I don't know what. I don't like the theory very much, but some people think that someone arranged these numbers specially, the big designer in the sky, to arrange these constants to give us the world we have, and that world would eventually produce human beings. And so that's it. Anyway, that's a little bit of background on Fred Hoyle, why he's famous. He then made a lot of errors of judgment in his interaction with people, which we all do, but he made more than others. Basically, most of us make friends and some enemies, but he made a lot more enemies than friends, and that's not a good idea in general. And certainly not a good idea if you want the Nobel Prize. Someone has to propose you for the prize. And the curious thing about this is that Fowler received the Nobel Prize for that measurement, and Hoyle did not, although he predicted it and told Fowler where to look for it. And that's another story which I don't want to get involved with, because I don't know much about it. But it's an indication of the fellow that he really complained a lot about various issues in science, and at the end of the day people got a bit annoyed about it. But one issue that he addressed was the origin of life as we know it. And it's quite interesting that he wrote a very popular science fiction book. I don't know when this was written, but I read it when I was at school, and it was called The Black Cloud. Has anybody heard of this one? It is a very interesting book, and I read it and enjoyed it. And the idea was that in space there were sort of organisms in space that came together as a huge black cloud and had a network, and it was so huge and it had intelligence. Okay, it's a very interesting thought. And it seems to have permeated his later science. And that's what I was going to talk about. Because around the time that I started to do radio astronomy and detect molecules in space, and by that we studied rotations of molecules in the laboratory. And you can take a radio telescope and tune them to those frequencies. For instance, carbon monoxide, as it rotates, it gives out a radio frequency, and you detect it using a radio telescope, and you can show there's carbon monoxide out there, and you can show there's alcohol out there. And if you came to my course last time, you know they can show a lot of other molecules are out there. So around the mid-70s, we had detected some quite long carbon chains, and in the newspapers it said we had discovered the key to the origin of life, and out there are organic molecules in the vast dust clouds between the stars. Only one simple step would be needed to change these into the molecules of life, and these sorts of things. So my work was a little bit of a stimulus to people who were thinking about how the biosphere arrived. Where did the organic molecules that ended up on the Earth come from? And I was moderately happy with that because it got on the front page of the Times, and so I was quite happy. But I wasn't too happy about the fact that in there, this fits with the theory of Fred Hoyle, if I look down the column a little bit further, who had been suggesting quite a number of other things, and this is where we come to the problem that I wanted to address. And he was saying that, first of all, he started off like, we see a particular band in the UV, okay, and wow, this fits with chlorophyll, or polysaccharides, just a band like this, and it just fits. And there were others rather similar to that. And the point is, he didn't fully understand that when we made a measurement in the laboratory of, say, a line in the laboratory, we could measure it to something like, well, let's say 36,000.01 megahertz. Okay, we could measure it very accurately. But when from infrared data, you get a broadband, and you measure an infrared band at 1,000 wave numbers, it might be 50 wave numbers wide. And when you see this, you see a band here, but you see another one there, and this might be, I don't know, maybe a CH stretch, and this may be an aromatic. So this is, you have these fingerprinted pictures, and you say, okay, this is in the right place. This is there's another one here. Yes, we take 4 or 5 with these measurements, and then we're fairly sure we've got the compound we're interested in, and that's the fingerprinting approach to the infrared. Not for Fred. He just wanted, oh, okay, we've got this peak. And then he started to look at these peaks. And the particular one that I'm going to discuss is a set of papers which are in the literature, which he said that he's got bacteria. He has through the infrared spectrum of bacteria. Okay, and what he has is something that looks like this, and it's about 3.1 microns. Okay. Now, to me, it looks a little bit like the silhouette of someone from the Ku Klux Klan, but it certainly isn't anything I wouldn't expect from bacteria. But I would expect something rather similar from every organic molecule I can think of, because this is the CH stretch frequency. Okay, that's exactly where the CH stretch frequency. And you can look in the catalogues of infrared spectra, and you will see thousands upon thousands of spectra in that, and one will be like this, one will be like this, one will be like this, there will be some like this, and you know then that basically all you can say is if you get an infrared spectrum in the laboratory that looks like this, you've probably got an organic molecule with a CH in it. Okay? That's the situation. So I'm young. I used to be your age, believe it or not. I used to have hair like some of you guys.
So
And,
did he detect that from radio telescope?
Well,
yeah.
No, let me tell you what this is. Okay, so because this is totally unscripted, so I just want it to be like that. Yes, good point. This is a measurement in the laboratory of bacteria. Okay, so he says. Okay. So, but let me talk about bacteria in space first.
Oh, good.
Bacteria in space is, I suppose, a relatively acceptable idea. It goes back a long time. Some people would say it goes back to things like medieval times, because people used to think that when comets came, that they used to have bring pestilence and plague. Okay, that somehow from comets down came showers of things that caused all these things. The most famous early name associated with this idea is Arrhenius, and it was from his time called panspermia. The idea is that somehow life occurred somewhere in the galaxy, somewhere in the universe, and then sort of permeated throughout space. Okay. It's difficult to know how that got there, because the conditions in space are very hostile. I mean, if you go out, the UV from the sun is pretty fearsome. I mean, you will not last. In fact, if you talk to Michael, he doesn't think that any astronaut will survive going to Mars. And I think
Michael Kasha?
Huh? Michael Kasha, yes. Because of the cosmic radiation that will occur over that period of time. And in fact, if you're flying airplanes, you know, cosmic ray get into the airplane. And that's why I'm a bit senile now, because I've seen too many airplanes for my time. But it is a serious issue. So if the bacteria are floating around unprotected, okay, then they will really have a hard time lasting for very long, certainly in regions near the sun, okay, in the solar system. But that's another part. So anyway, there's this, I think, fairly reputable idea by Arrhenius and other people that maybe if life occurred somewhere, it somehow seeded the galaxy. Perhaps it could come in a meteorite, you know, stuff in a meteorite and then be protected. And for instance, there is evidence, I'm accepting this evidence, it's tricky to accept, but there are rocks on the Earth which come from Mars. How do they happen? Then you get a meteorite or something hits the surface of Mars, it blasts it out into space because Mars is much lighter than the Earth, so some of these rocks, then the sort of velocity of this sort of catastrophic event is enough to get them into free flight, and some end up on the Earth. These are collected, as I understand it, in Antarctica, where there are ice flows that pass between mountains, and so vast areas come to a sort of narrow place, and they pick them up in a particular area in the Antarctic. And that's where some of these rocks that you might have heard you might have seen in the general scientific literature that some people found evidence of bacteria in these Mars fossils. That's a fairly contentious one, and I'm not sure. I think it's difficult to prove that. There are some interesting. Yes.
I was just going to ask, how did they know that those are from Mars?
Yes, they apparently are linked to the findings that people have made of Mars material. That's from the Mars landers.
Okay.
Okay.
Mm-hmm.
Okay. So
I was always curious.
It's reasonable.
Mm-hmm.
And again, in science, you mustn't ever accept what another scientist says. You must say, well, you look at the credentials and say, well, yes, he's done the best he can, or she can, and that in my case, I've tried hard to understand the issues I'm going to discuss, and I've done the best I can. I can give you the evidence for what I'm going to tell you. And so, yes, go ahead.
You could finish what you were going to say. Oh, so to get a rock from Mars on Earth, it would have to be huge leaving Mars, because by the time it gets to Earth, would it be like...
No, apparently not. These are small rocks, and in fact, apparently, although some of them do come in at high velocities, some of the smaller ones apparently don't come in at these very high velocities, which cause them to... and the center of them apparently often is not... I understand. I mean, I had the same thought as you did. Wow, don't they just burn up? Not all of them burn up. Some of them actually get to Earth, and they don't necessarily get that hot. I suppose I'm guessing that the temperature depends on how large they are, and they're in the velocities that they have are presumably, in some cases, I don't think they're very high. Okay, and that the bacteria can actually continue to survive on the inside. I'm told that inside some of these, the meteorite doesn't ever get, it's only the surface that heats up. Yeah. Okay.
These
okay.
are igneous rocks or something that...
I'm not an expert.
So
if you want the real answer to that, I'm going to get around. I'm trying to... this is the thing with the origin of life. Everybody knows something more than I do about it. But anyway, to cut a long story short, how did I get involved? Apart from the fact that as a microwave spectroscopist, I was making measurements on half a dozen lines in space and could be very sure that what we detected were these simple carbon chains. Well, Hoyle started to produce these papers, cellulose in space, polysaccharides in space, and he did these mainly together with a colleague called Vikrama Singh. And the papers, if you're interested in them, are basically often Hoyle and Vikrama Singh, who is professor of mathematics at Cardiff, and Fred Hoyle was, I think, the professor. I'm not sure. He may have been the professor in the chair that Stephen Hawking has now, but like the same. I think he may have had the same chair that Newton had, or whatever. So he's a pretty big shot at the time.
At Cambridge.
One of those, Oxford. They all look the same to me, Anyway, so these papers came out around the mid-70s to 80s. And I was looking at this thing, and I could see that there's very little information here. This is 3.1 microns. Even in the first year, organic chemists would say, this is a carbon-hydrogen compound, okay? You can't say much more. But what he said is you take freeze-dried bacteria. I saw him on television. Said he went down and picked up stuff from a lake, and they freeze-dried it, and they got this absorption spectrum. And it was in wave numbers, reciprocal centimeters. Now then, in comes the astronomers, and there were some measurements that were made of emission. I think these were emission from a star. Okay, so you have a star, and there's some material around it, and there's emission from the star. So okay? So this, and this spectrum, which I'll just draw like this, was something like so the center was, for argument's sake, it's like this, okay? And this was linear in wavelength, because astronomers work in wavelength, angstroms, say. And the emission was in watts per square centimeter falling on the detector, because that's what you got. You got coming in through a spectrum. And this was something related to, well, alpha, the absorption coefficient, whatever. So this, so here are two measurements. Okay. Now, let me just say that the whole of the spectroscopic community, from people like Hertzberg, who was the father of spectroscopy, Nobel Prize winner, the person who wrote all those wonderful books on spectroscopy, were just in horror at these measurements. I was not the only one, okay? But I was a young scientist, and I just liked mavericks. I said, oh, you know, 2 fingers to the establishment. I mean, you're a young guy. The one thing you like is someone like Fred Hoyle telling the establishment, they're idiots, right? So I warm to that. I like to see people who's now. But now I discovered he was telling me I was an idiot. And I thought, well, I don't go for this because I understand. I mean, I don't understand very much, but I understand something about spectroscopy, and I know that if I took all the organic molecules that we already knew, maybe we knew 50 organic molecules with carbon, and added them together in some sort of, with this set of sort of contours, I could probably come up with hundreds of different sort of ways of producing this sort of shape. Anyway, what happened then? What happened then was I started to look at this paper, and what happened was that Hoyle produced a paper which compared this spectrum, which was the observed spectrum, astrophysical spectrum, with this spectrum. Now it's difficult to do that because one, this is watts per centimeter, it's in emission. Okay, all right. This is in wavelength. Well, wavelength to wavelength is just a reciprocal. So I thought, well, I can say, but let me just do this transformation myself. So I looked at this and I thought, well, I don't know quite what the y-axis should be, but I sure as hell know, well, if I know this wavelength, I know what it should be in wave numbers. Now, what Hoyle had done is published a paper with chromosome, and it actually had this spectrum. Okay, and they were, I don't know, it was dotted, right? Something like this, compared. So this was his proof, okay, that there was an almost exact overlap between the astrophysical spectrum and his spectrum in the lab. Okay. And at first I didn't realize that here was something glaringly obvious, and it was only later that I realized that there was something not right. But I decided to look at this. I said, well, let's just check what this is. So I measured this in wave numbers. I discovered it wasn't in the right place. It was somewhere over here. All right. Now, in those days, we didn't have computers. You know, well, you guys had computers. Well, we did have computers, but we didn't have them. So actually, the way I did this was I Xeroxed this and put it on an overhead projector, and I put it up on the wall, and I expanded it. And I was rather pleased with this technique, and I was able to actually check all this out in analog without a computer, that these things were not in the right place. But anyway, to cut a long story short, I started to replot this myself, and they were not in the right place. So in the transposition, I realized that though the dotted line was not right, it was somewhere over there. And so in going from wavelength to wave numbers, one of them, or both of them, were professors of mathematics. They didn't seem to be able to take a reciprocal. So I thought that was a bit odd. And in fact, there was a co-author, so I suspect they would shift the blame to them. I'm not going to. I don't think. I mean, maybe graduate student, undergraduate, but anyway, it was. And I'm not going to. I don't give any blame to him at all, or her, because if you're a professor of mathematics and you produce a paper in which the reciprocals, you can't even show that you can do a reciprocal, I think there's a problem. But anyway, that's by the way. And I looked at this, and I said, well, the data are shifted. I'll now digress into something which is certainly something's on the record somewhere, is that I was contacted because I did try to publish something on this, and it disappeared some strange way. I don't know, but anyway. It disappeared. These things disappear. I don't know.
You never heard back from the reference.
I sent it to a journal, and they thanked me, and it never came back. And at the time, I was in the middle. This was about 1988, and I was in the middle of the C60 controversy, because at that time, which we can come to, that people didn't believe C60. So
You've been there.
I've done my time, so I didn't worry too much. But anyway, the BBC decided to do a series on famous people in the UK. They were called Imagined Worlds, and they picked Fred Hoyle, and they asked him, each of these people, what were their three great contributions. In the case of Fred Hoyle, he said this, and he showed this spectrum. Now, I had already discussed this with the people who had done the research for this, and told them that these weren't in the right place. And I was not the only person. A Dutch astronomer, who since died, he discovered it too, and another astronomer, a radio astronomer an infrared astronomer from Lancaster, also discovered that they weren't in the right place. So I wasn't the only one, for what it's worth. Anyway, in the film, when they were recording it, the person who was doing the interview with Fred Hoyle said, well, one scientist says the data are shifted. And Fred, who's a Yorkshireman, he said, the man's a liar, right? So the BBC then came and contacted me and said, we'd like to keep this in the program that we transmit, but we see there's a problem here, and we need your agreement. So I watched it, and I saw the final edit, as I thought, and I was very happy with it. I said, that's fine. It didn't actually name me, but everybody in the community knew, science, chemistry, and certainly in the astrophysical community knew who that person was, which is me. And it was right at the beginning of the program, and he was so flustered, it actually basically destroyed his arguments completely, the way it was cut. And so I agreed to that. And then when the program came out about a year later, and I was still embroiled in C60 stuff, they re-edited it, so it was a very minor part, and I was very angry. They kept it in, but I wanted it to destroy the credibility of his arguments for bacteria in space. Because if a very famous scientist, such as, say, Einstein, said, I have got proof of bacteria in space, you can imagine how many people outside the scientific community accept that and will say this. And I was very angry, and most of the scientific community were about this. So I was a bit cross, very cross, but I was so embroiled that I didn't bother to follow it up. And so, for what it's worth. However, all that being said, there's a very fundamental flaw here, which I didn't notice until I looked at it more carefully. And that is the error bars. These error bars are such that from the experimental data, this is the important point about it, the experimental data are such that whenever you do this experiment again, there'll be some distribution, maybe a Gaussian distribution, it depends what you take. And so, basically, if you put this through this, you can get a straight line through here, and it will still fit. You see what I'm saying? Even if the origin of this spectrum is bacteria. This shape has no information in it because the error bars are so great. And so there's a fundamental error here. The possibility of it fitting through here shows that there's a fundamental scientific problem. And that is, why did they go through the center so well? And I do a very simple test. Now you can take a Gaussian distribution, but let's take a very simple test, okay? Let's take this, and just for argument's sake, we'll say split it up into three, each one of these into three segments like this, all right? I mean, I've accentuated it, but nevertheless, you get the idea. We can do a very simple analysis of this and say, well, let's say it should go, for argument's sake, it could be in this box, that, but because of the error bar, okay? So the probability of it going into one of these boxes is only 1 in 3. The probability that the next time you do the measurement, it is again about the same, so it should be there. So the probability of it going through the central box, okay, 7 times in succession is 3 to the 7th. You see that? That's the thing that Naresh wanted me to explain to you.
That I really was impressed.
And the point about it is that if you do this, my estimate from very simple study, I mean, I was starting to do Gaussian and stuff like that. I thought, no, just do simple. My estimate is that the probability of the observed spectrum, because of the error bars, fitting exactly with the spectrum in the lab was about something between 1 in 1,000 and 1 in 10,000. And that's science, and a scientific issue about experiment. And I think I really like that.
Yeah.
And I think it's something to do with error bars. I mean, you know when you're a kid at school and you think, oh, well, the teacher's always scoff, what are your error bars? Well, that's so... But in the end, when your reputation depends on it, it starts to be rather important. Now, let me tell you the next part, because this is historically what happened. Halley's Comet came along, which you all know about. And there were papers on Halley's Comet and the spectrum of Halley's Comet. And they're in Nature. You can go back to the famous Nature paper. And there was a lecture, a seminar, or no, a conference at the Royal Society in London, to which I was invited. And Hoyle was there, and his colleagues. And lo and behold, the comet has a spectrum rather similar to this, and it's got a little thing and it fits a little bit well. And he came up with this spectrum that I had reanalyzed. I couldn't believe it, that he was prepared to go there. At the same time, for those of you who are interested, one of the most famous American names associated with comets is Whipple, W-H-I-P-P-L-E, who had, I think, the first person to suggest that comets were icy snow balls. And Hoyle was claiming that this was not right. These icy snowballs, that comets were really organic stuff and this, that, and the other, which is fine. I mean, it may or may not be right. But there was, was a lot of, I don't know why scientists get so excited about these things, but they seem to, But I think one thing is that their reputation is dependent on what you've written, and your job and things like that. But I think people should understand that science should be allowed to make mistakes, but they must admit them. All right? That's the most crucial thing. And to give you a little bit of an aside of my own attitude, when we suggested that the measurement you weighed of a carbon molecule with 60 carbon atoms was C60, my attitude was the following. And that was, well, I think it's a good idea, I think it's adventurous, I think we stuck our neck out, but I'm going to spend the next 5 years trying to prove that we're right. And that would be great. But I also thought, if we're wrong, I would like to be the person to prove that I'm wrong. I didn't want anybody else to And I think that's the way one should be. I do not agree that scientists should throw out lots of ideas, okay, let other people prove or disprove them, and then try to take the credit for that. And that I object to. I really do object to. And Hoyle was this sort of person, because you care, oh, he's such an imaginer, who else would have had these wonderful ideas? Well, lots of people, but lots of people wouldn't use their reputation to foist these ideas on the general public. And so that was my attitude. And when in fact we were very close, in fact we actually had extracted C60 5 days before I got the manuscript for C60, so I'm very proud of what we did at Sussex in that area. However, that general situation, so I'm sitting there listening to this talk, and Fred Hoyle comes up and gives this, and says, now, okay, and now what you find is something similar coming from CH, the CH molecules coming off Halley's Comet, which we already knew already. You only have to look at spectra 50 years ago to see CH and C carbon molecules in comets. That was all known. So it's not at all unreasonable to believe with NH there and water coming off the comet that the comet will have something in the 3.1 micron region. But he says, now we've got evidence that there are bacteria coming on Halley's Comet. Unbelievable. So at this point I got up because I'd been asked to, and I had my data. And I said, well, let me go back to this astrophysical data, and I then showed that, in fact, that I don't get the same transformation. I mean, I decided to confront him with this in the full audience of the Royal Society. And I put these down, and Fred jumped up, as he tends to, and said, where do you get these data? I said, I got them out of your paper. Uh-oh. And he was stunned silence. I said, I've transformed this myself correctly from wavelengths, and there's an error, or whatever. I said. And he just stood there, and he then said, well, it must have been a draftsman's error. At this point, you know, the rustle of, you know, I mean, he only realized suddenly what he'd said, and he then sat down. And at the time, there was a film called by Peter Greenaway. I don't know if anybody knows of Peter. They're a very unusual film. It was called The Draftsman's Contract. And I wish I had the nerve to say, are you sure it wasn't the draftsman's contract? You know, and I think that would have been pushing it too far. However,
What was the film?
Huh?
Are you going to tell us about the film a little bit, or what was the idea in the film?
no, it was just the name of the film.
Oh.
No, the draftsman's contract. I don't think it was, but I think I don't know, have any evidence. I just have a feeling that somehow maybe the young student who was working with it didn't know quite how to do the transformation. There were no computers around, and
His name was not on the paper.
Well, his name was on the paper. Yes.
There were 3 authors.
There were 3 authors on the paper. I decided that I'm not going to give. I think Hoyle, most famous British scientist at the time, and another one who's a professor of mathematics, should take full responsibility, and they should have checked the students and also shown him how to do the correct transformation, if indeed he did that. So I'm not going to give any blame to the student in this case. However, then I really got very angry because I read the write-up to the discussion, and the people at the Royal Society who were the conveners of the conference totally censored that discussion. So there's no record, and I think it's an important issue in science that whatever goes on, they should not have censored that discussion. And to give a historical analysis, doesn't compare with it, but I think one of the most famous quotations of a discussion after a conference or after a seminar is to be found in the altercation between Bishop or Archbishop Wilberforce and Huxley after Huxley made a presentation on Darwin's theory of evolution, which if you haven't read it, go to Google and put in Huxley, Wilberforce and chimpanzees, and you'll find one of the most erudite sort of rebuttals it. I can't remember what it is, but basically Wilberforce after this said something to Huxley. Is your relationship with a monkey through your mother or your father's line or something? He thought he was into it, but Huxley's was just fantastic, and I'll let you look that up. And it's almost certainly on Google the first thing you can get, and a brilliant riposte. And I only wish I were equally eloquent in coming up with something which has stood the test of time. But what I was going to say, a few other words, how are we doing? Just a few minutes, about what I call pathological science, or what is called pathological science.
We have at least until 1:30 or more.
At least we've got 1 hour's worth of camera. But I thought there are a number of issues, and I think it's quite rare in science. There is a very recent one, which I'm sure all of you know about, the AT&T, the Sherman papers, which are superconductivity and everything you can think of. I mean, I think it's been raging, and it came to a head when it was discovered that one of the diagrams had exactly the same noise. I mean, you and I know that when you look at, you get something like this, but the noise is no way that the noise can be the same on 2 of these papers. Yes, go ahead.
Was that the guy that was, he published it and he's got in trouble in Germany for his degree? Okay.
Yeah, this is Sherman, and I watched these papers come out. It was very exciting because C60 was superconducting at room temperature or something like this. I thought, wow, well, we saved the world, And I read some of the papers, but it was really outside my field, so I couldn't tell really what was going on. But it was really solid-state physics, and it took some outstanding physicists who tried it. I know one, senior physicist. In fact, I think he's now the president of the whole University of California system. He said that they looked at this very, very, very carefully, and they could not reproduce it. But they just thought, well, we don't have the right conditions. So it took a long time to find this, and then I think a woman found that the noise was exactly the same on 2 totally different spectra, and that was a no-no. So my feeling is that Sherman really was, well, not quite there, in the sense that something as important as that was going to be discovered. I mean, it's going to be shown that it was false. Okay, he appears to have cooked the data. That I don't consider, that's going to be happening very occasionally. I don't remember another case like it. Maybe there are going to be cases that these are cooked in very unimportant areas and they take a long time to find out. But in important science, if it's that important, superconductivity at room temperature is going to be found out. People are not going to be able to reproduce it. Perhaps the most famous recent case is the cold fusion case, which I think now comes to my final point, and it's one that's made in one of Richard Feynman's books. Very simple one. In the case of that, my analysis, and I think the analysis of 1 or 2 other people, is that, well, I think the idea of this muon catalyzed fusion and this type of fusion was around. Okay, there are, it's not, as I understand it, there are people who had been thinking about it. And there was apparently somebody in one of the universities in Utah who had been studying this for some time, and they'd got some funding for it, but it wasn't getting anywhere. It's electrochemical, trying to produce conditions in which fusion would occur. A funding advisor said, well, you should really go and work with these other 2 guys at the University of Utah. And they got together, and as far as I understand it, there was an experiment, badly constructed with a big peak there. And maybe they just saw, save the world. I mean, 3 deadly sins: save the world, lots of money, and Nobel Prize. I mean, that's what they were looking at. I mean, if this were true, they really had free energy, more or less. Right? They had money to burn and the big prize, which is, has downsides to it as well. And as far as I know, they didn't publish in Nature or whatever is where you should. They published on television. Because I saw this. I was in the States at the time, and I'm sitting in my hotel room and I'm seeing a couple of guys, one of whom I was familiar with. It's a British scientist from Southampton, a very reputable electrochemist, standing there saying, we've discovered this. Well, of course, it took about 2 years for, I mean, some people were very skeptical. Others said, let's try this out. Of course, no one was able to show this. As I understand it, there is still money being put into this. Now we come to the crucial scientific bit. The point about it is that if they saw cold fusion, you can never disprove that they didn't see it. However, there's a little rule, and it's my rule, and that is that if you do an experiment, you do some other experiments to show it, okay? And if only 1 out of 5 show you come up with a result, then you're almost certainly wrong. If 4 out of 5 say you're right, then you're almost certainly right, and the 5th one doesn't, you've got to check what you did there. In their case, no one has ever been able to come up with it. And the point is that if you have an effect as a scientist, what you do is you see this result, and I had it, I remember when I was a young student, I thought, wow, my first result. I went running around, actually got a result after 1 year of misery, and blowing glass and all this stuff. And then I did the experiment more carefully, and it went away.
You won't tell us which.
No, it was I don't know. Oh no, it's not. I didn't publish it. Right?
Oh, okay.
No. I mean, I was. You see, when I was a PhD student, I was a spectroscopist, and I did several projects, and it took a year before I got a result. Okay, and I got my first result, and then I did the experiment more carefully, and I couldn't reproduce it. And what has happened with the cold fusion people is, well, it's weaker than we said, and it's weaker than that. And the point about it is, doesn't matter how carefully you design the experiment, you can never disprove that to some degree that cold fusion effect doesn't occur. All right? You see what I'm saying? And the point about it in science is, as you design your experiment more and more carefully, if it's a real result, it gets stronger. Okay? And that's what happened with C60. As we worked on it, and we used the experiments every time we got C60, it didn't go away. What happens with an experiment, you know, you get your PhD or your PhD in 5 weeks instead of 5 years. Whatever, you know, you got this result. And then you do it and you discover that as you design the experiment more and more carefully to home in on it, it's not there. And that's very common, very, very common. But you can never show that it isn't there, and somewhere within the noise level. And that's the problem with science, and that is the get-out clause. And that's, as scientists, I think, the best thing you can learn is that basically the experiment, the real experiment, as you design it better, it gets more and more obvious. But the one that probably is wrong becomes less and less obvious. Get rid of the noise level, it goes down. Well, it can still be down in the noise level. There's always noise in most experiments. You're looking for a spectrum. Okay? And there are lots of cases of that. And so that's today's story. Any questions? All right. I never even prepared that, but I don't mind. Anybody, any questions?
Wonderful. I think the conclusion that if you get a peak in some spectrum that you're excited about, try to repeat it and with more careful experiments, and if it becomes smaller, they are almost certainly wrong.
Yeah.
I have a question about that spectrum that they were presenting. How far was the shift? I mean, it seems like...
Enough. Okay, yeah.
Okay, so
I mean, unfortunately, they're all in the file. I've got a box, a Xerox box called Hoylerama. Okay, it's all in there. And I was going to publish it, but I just thought, why don't I give this talk and put it on record so I don't have to write the damn thing up? because the thing about it is that when you have a reputation, you have a responsibility, as I have. Right? I feel a responsibility because, rightly or wrongly, people think that what I say. I mean, I hear that they think, you know, I'm smart. Well, I know I'm just me. I'm not any smarter than you guys. I was very lucky. I'm a good scientist. Not necessarily a better scientist than anybody else in this room. Probably not as good. But I was very lucky. I can do something. I struck lucky 3 times, and very lucky the 3rd time. But the important thing is some sort of scientific integrity. You know, I mean, in the sense that if you have the position that Hoyle had, and he had the position of someone like Richard Feynman, in the UK. I mean, he was that famous, okay? And so if Feynman says something, you know, that people listen to it because he's been right a lot of times, and Hoyle had been. But he just went too far. And in this case, yeah.
What happened to him after the talk you gave?
What?
What happened to the after you gave the lecture? Did he just kind of drop off the face of the earth, or I don't?
He never went. I don't think he ever. It's a good point. I didn't follow that. He didn't go off the face of the earth. What really happened is he was then pretty elderly. I mean, it was just a few years before he died, and I didn't want to hound him anymore because, you know, but he did write things about me, very unpleasant things when I was a young scientist. I mean, he said something at the unfortunate year, because at some, yeah, I remember it. I was rung up by a newspaper, and I said, well, you know, even a first-year organic student would say, you know, this is a CH, but you can't tell which CH molecule it is, let alone bacteria. Right? So that got picked up by the newspaper, and this guy wrote it, and Hoyle realized, I think, that I said that. He said, the unfortunate first-year organic students who are unfortunate enough to be taught by Dr. Kroto, right? You know, so, but, you know, he didn't, well, but he was much quieter. He was then getting on, and I think he realized that he'd got a real problem, because he probably went back and realized what a mess he put himself, because this is a fundamental scientific mess, this error bar. This is a fundamental scientific mess. Yeah.
But he never accepted his mistake?
Pardon?
Did he never accept it?
I don't think he's the person who could accept a mistake. There do seem to be scientists. The most important thing you can ever learn is that you're going to make mistakes. And if you accept that, and when you do make a mistake, you accept it. I mean, let me just say, I did make a mistake. I'll tell you, on the first paper I ever wrote by myself, there's a you know, the square root, plus or minus the square root of, in a perturbation formula. I got the sign wrong. And this is a very beautiful paper. I'm so proud of it. But I got the sign wrong, so I got a little shift. Instead of it being in the second order perturbation term. And so I shifted the wrong way. And a friend of mine, Anthony Mehrer, who was a fantastic spectroscopist, he wrote to me, he said, Harry, he said, I've been looking at you know, it would be Anthony, because he was a very meticulous guy, outstanding spectroscopist. He wrote to me from Vancouver, right? So I'm at Bell Labs, and I get this letter. I think you got the sign wrong here. I looked at this, and I thought, you know, I'll never make a scientist, you know. And so I then sort of had to accept that I'd made a mistake, okay? But it was such a little one, but I thought, you know, I really felt the heavens had opened up, and a big, you know, in Monty Python, a big 10-ton weight had dropped on me and squashed me into the ground. What I have learned is that human beings are fallible, all right? And it doesn't matter who you are going to make mistakes. And the most important thing is to accept that. And then say, well, I'll try to do better next time, okay? Hoyle was incapable of doing that, and he's very famous for the steady state theory. I mean, this is probably, I mean, I haven't talked about it, talked to any astronomer about the steady state theory as opposed to the Big Bang theory. I mean, most people say, well, the evidence for the Big Bang is pretty good, and certainly much better than steady state, but he never ever gave up the steady state theory, and that's what he's perhaps most famous for, not this one.
Harry, what is more phenomenal, the shift? The shift could be, or the error analysis?
The error analysis, by far.
That really killed it.
That kills it in a very important scientific way. That even if the astrophysical data were bacteria, the next time you do this experiment, they'll be at some other point on the error bar. You understand? And therefore the fit, even if this fit had been here, the next time you make the measurement of the observation, it should be somewhere else on the error bar at some statistical distribution, different from where it was.
Yeah.
That's the important, and from a scientific point of view. And it's a very nice one. Difficult for me to, you know, I'm not a mathematician, but I think you can all see that. And I think that's what science is about. Science is about feel for why things are the way they are. And that's the question someone was asking about politicians, or was that? Yeah. Politicians don't have that. And only scientists have that. They get a feel for these things about global warming, okay? You know, let's look at they have a feel how difficult this is to actually pin down. And then, of course, because you're a scientist, you let the politician off the hook. Because you can't go there. I mean, the worst thing of all was there's some guy on fingerprinting in the O.J. Simpson, and he was run rings around by the lawyer, who knew. I mean, this guy had never been in a court of law before. The scientist was right, but the lawyer was able to point out, well, you know, it could be 1%, this, that, and the other. That sort of situation, you can never prove it, and the scientist knows that. And there's a famous line, I think, Truman, give me a one-armed scientist. Why is that? Then they won't say, well, on the other hand. And it's true. But that is our strength, not our weakness. And that's the problem. Most of the people outside the scientific community do not see that as a strength. They see that as a weakness of the scientist. But our strength is to know that we're uncertain. And the worst thing you can be is to be sure of something. Because I'll tell you, in science, once you're sure of something, sure as hell, nature will come and say, you shouldn't be quite so sure. It always comes up. And I found, wow, I don't understand this. And then it comes along and says, you don't fully understand. You understand some of it, but not everything. And I think that's the strength of the scientist and the weakness of almost everybody else, particularly politicians who said, I know what to do. And they don't. And there's lots of evidence for that.
Was this spectrum ever run more than once? Or?
That's an interesting question. I wonder, I don't think they ever did, no. Because they just published it, and they wrote books on it, and they always showed the same spectrum. In fact, there's a book called Proof That Life is Cosmic. And of course, if he's right, if he were right, it was Genesis, in a sense. Life came from outer space.
All right, this is a chance to ask Dr. Kroto more questions.
Yeah.
You mentioned earlier that there are downsides to winning the Nobel Prize. What are some of the downsides of winning the Nobel Prize?
Yeah.
Giving lectures like this.
Yeah, everybody asks.
Let me tell you something. The curve is like this. This is the curve of my life. Happiness this way and misery this way. Okay. This is what it should be like, a bell curve, right? And a bit of this, and in the middle, you know, somewhere. Well, after the Nobel Prize, it's more like this. Okay. Like a Batman thing. And it's true. There are lots of things that happen. The first is that it totally changes what you think you're going to do. I mean, I was a very happy scientist. I really was pretty happy with my science before the Nobel Prize. Or before the discovery of C16. I was satisfied. I've done some really nice work. I had 2 areas in radio astronomy and phosphorus I was very pleased with. And I thought it would be nice to do a 3rd thing, but you know, you can't. Three nice things, and then we got C60, and then, you know, wow, we know this might be the big one. And I don't know, it's 1%, 10%, 50%, but in the end we did. Whether it's worth it, no, I don't know. But now I feel some responsibility. I mean, kids come and ask for my autograph, fine, I'll give you that. Michael said, don't give them. He said, mine's more valuable than yours. You give them, you go through it. I'll sign it. I'll sign the neck of somebody like this. But I feel that young people particularly think that maybe I have something worthwhile saying. And I feel the things I feel strongly about, I'll say that, in such as these, you know. But also, I get too many invitations and I can't say no. And so it's really completely perturbed my home life, personal life, and all things. And I really wanted to go into graphics and design and stuff like that. So I never got to do that. And I'm here now doing more research. Your fault, Naresh.
Well, I accept it.
Well, it's always when you've done it. So, yeah. So there are downsides, particularly involved. Not for everybody. Some people say, you know, just fine, doesn't make any difference. But I just feel that I've got a certain responsibility to represent many of the scientists who feel the same way that I do about funding in science in the UK or here, about issues about scientific reliability and the way politics go. And also, I've got the Vega Science Trust where I make programs, careers programs for scientists. I do feel strongly that everybody should understand science better, because science and technology underpins 99% of our lives. That goes right, and that we are facing sustainability and survival issues. And I think that it'll make them aware, and so I do say things, but to politicians and people who are in charge of science, and they don't want to hear. But You know, I'm only one person. I don't get everything right, and and I tell you, when you get into that situation, they don't sure as hell tell you when you got something wrong. You know, so I try to be right. So there are some. I mean, I'm not being totally facetious about this. It's obviously very excited about the things, and but there's nothing much in between. You know, life is a bit hectic. Is that okay?
Yeah.
Don't win one. It's nice for
You don't have a choice.
No. Well, what I wanted to say was I had no desires to win prizes. I mean, I didn't go into science to win prizes. When I did some nice, I thought, oh, well, maybe this is good enough. Then we got C60. I thought, well, you know, this might be. But before that, I was absolutely happy with my work. There was no chance that anything that I'd done won the Nobel Prize. And in fact, my phosphorus work is much better scientifically than the C60 work. Okay, so I think that's an important. I want to stress that until the discovery of C60, I was satisfied with what I had done. I was a professor. I'd done some nice work. I thought it'd be nice to do three nice things of commensurate stature. I never for a minute dreamed that we would discover something so serendipitously or so unexpectedly as C60 that would propel me to where I am. Whether I should be here or not as a Nobel Prize, it's not for me to judge. But you know, I can think of some fantastic scientists who won't get the Nobel. Really unbelievably bright, done some brilliant work. So I feel a bit difficult about that when I know these guys are so much smarter than I am. But yeah, that's the way, you know, life's not fair. I mean, I shouldn't have. I wish I hadn't. You know, no, I'm only joking. But you've asked a nice question, and I hope I've given you as complicated an answer because it is a complicated answer.
Thank you.
Okay.
The tape
must be long.
Yes.
Kroto again. We go for lunch afterwards.
Were you going for after?
You must not have lunch.
No.
You didn't have time to.
Okay.
Well, I'll spend a few more minutes with the class.
Okay.
And I'll